네, 안녕하세요. 다들 접속 중이시니 잠시 기다리도록 하겠습니다. 네, 다들 접속 중이신데요. 조금 더 기다렸다가 시작을 하도록 하겠습니다. 네, 안녕하세요. Good morning. 네, 이제 어느 정도 다 접속을 하신 것 같습니다. 자, 그럼 오늘 웨비너를 시작해 보도록 하겠습니다. 안녕하세요. 저는 윈지디 코리아 마케터 신준엄입니다. 오늘 윈지디 코리아 테크니컬 웨비너에 참석해 주셔서 감사드립니다. 김성당 선무님 발표 전에 플랫폼 사용 방법에 대해서 간단히 소개 몇 가지 드리고 시작을 하겠습니다. 일단 참가하신 모든 분들은 자동적으로 음소거 처리가 될 예정입니다. 원만한 진행을 위해 음소거 처리가 되니 양해 부탁드리고, 저희가 듣지는 못하지만 오른쪽 화면 채팅방을 이용해서 실시간으로 확인할 수 있습니다. 또 질문을 남겨주시면 발표가 다 끝난 후에 Q&A 세션 때 답을 드리도록 하겠습니다. 이미 오른쪽 채팅방을 적극적으로 활용을 하고 계시네요. 그래서 다른 분들은 보지 못하지만 저희 윈지디 멤버들은 볼 수 있기 때문에 자유롭게 작성을 해주시면 되겠습니다. 또 지금 보시고 계신 PPT를 조정하실 수 있으세요. 화면을 크게도 할 수 있고 작게도 할 수 있는데, 제 화면과 이때 PPT 화면 사이에 보시면 검은색 라인이 있으실 거예요. 그 줄을 잡으시고 아래로 당겼다가 위로 올렸다가 하시면 작게 했다, 커지게 했다 화면을 조정하실 수 있고, 또 오른쪽 톱니바퀴 상단에 옆에 보시면 그 화살표가 있으실 거예요. 그걸 클릭을 하시면 화면을 켜지게 했다가 또 작게 했다가 사이즈를 확인하실 수 있습니다. 또 채팅방에 혼자 계시는지 문의 주셨는데 채팅방은 프라이빗으로 설정이 돼 있어서 다 같이 공유되진 않고요. 윈지디 분들만 보실 수 있게 되어 있습니다. 또 마지막으로 발표 자료는 PDF 파일로 제가 곧 공유를 드리도록 하겠습니다. 또 웨비너 진행하는 동안 필요하신 분들은 다운받으셔서 발표하시는 동안 참고해 주시면 되겠습니다. 네. 자, 그럼 오늘 김성남 상무님께서 간단히 웨비너에 대해서 소개를 한번 드리고 시작을 하도록 하겠습니다. 상무님 준비되셨나요?
감사합니다. 예, 안녕하십니까. 윈지디에 있는 김성남 상무라고 합니다. 지난 한 해에는 정말로 코로나로 많은 힘든 시기에 우리들이 있었던 것 같습니다. 다들 안녕히 계신지 궁금하기도 하고, 아마 비즈니스에도 상당히 문제가 많았던 걸로, 좀 애로사항이 많았던 걸로 그렇게 느껴집니다. 그렇지만 그래도 변함없이 윈지디를 그리고 응원해 주시고 적극적으로 지원해 주신 모든 분들께 이 자리를 빌어서 대단히 감사의 말씀을 올립니다. 아울러 올해 한 해도 2021년입니다. 그래서 올해 한 해도 저희 윈지디가 기술적으로도 그리고 앞으로 영업적으로도 지원에 최선을 다할 수 있는 그러한 윈지디가 될 수 있도록 노력하도록 하겠습니다. 다들 알고 계시다시피 윈지디 코리아가 매년 진행해 오던 제주도에서 진행한 테크니컬 워크숍도 있고, 그리고 부산, 서울에서 하던 그 로드쇼, 그리고 커스터머 데이 등 많은 그 이벤트들이 있었습니다만은 그 지난 한 해에는 면대면 진행을 하지 못해서 대단히 아쉬웠습니다. 오랫동안 아마 그러한 걸로 인해서 또 비대면이라는 그 툴과 어떤 문화가 비즈니스의 어떤 한 모델로 자리 잡아갈 것으로 이렇게 예상은 하고 있습니다. 그래서 오늘 그동안에 하지 못했던 우리 코리아 웨비너를 오늘 이 자리를 빌어서 테크니컬 세미나를 갖다 준비하게 됐습니다. 그 하루속히 면대면을 기대하면서 오늘의 주제 발표에 있어서 간단히 말씀을 올리도록 하겠습니다. 첫 번째 주제는 마켓 업데이트, 그러니까 2020년에 윈지디가 했던 비즈니스 레코드하고 2021년에는 어떻게 또 그러니까 예상을 하는지 우리 글로벌 세일즈에 있는 카탈라미 까르멜로 제너럴 매니저가 발표를 할 것이고, 또 그 다음에는 다들 알고 계시는 ICER, 그러니까 XDF 2.0의 어떤 그 테크놀로지하고 또 퍼포먼스 임프루먼트가 어떻게 되는지에 대해서 조지가 발표를 하도록 하겠습니다. 그리고 근래에 아마 그러니까 레이티스트 인포메이션으로 해서 X72DF 버전을 우리가 좀 그 다양화하고 옵티마이제이션을 하고 코스트에 대한 어떤 컴패티티브니스 뭐 기타 등등을 위해서 그 72DF 1.0, 1.1, 1.2 그리고 2.1, 2.2에 관련돼 있는 그 좀 더 자세한 내용들을 알려드리도록 하겠습니다. 그 다음에 다들 알고 계시는 그 관심 있으실 부분 중에 하나입니다. 그러니까 얼터너티브 퓨얼이라 해서 카밍 얼터너티브 퓨얼로 해서 그 R&D에 있는 바이스 프레젠트인 도미닉 슈나이더께서 발표를 갖다 해주실 겁니다. 또 작년에 우리가 어나운스한 그러니까 숍 버전의 그 엔진 모델입니다. X52, X62에 대해서 그러니까 루디 웨스타인이 발표를 해준 예상입니다. 그리고 X92DF가 지금 나간 지 벌써 9대가 나가고 지금 이제 일단 서비스되는 엔진 모델이 있습니다. 그래서 어떤 오퍼레이팅 익스피리언스 관련해서 궁금하실 부분이 있어서 그 토픽도 주제로 잡았습니다. 이 주제를 통해서 발표자와 함께 좋은 시간 되시기를 바라며 저는 나중에 그러니까 Q&A 시간에 또다시 뵙도록 이렇게 하도록 하겠습니다. 그럼 제가 일단 마이크를 까르멜로에게 넘기도록 하겠습니다. 감사합니다. Good morning, Carmelo. Please have the microphone for your presentation.
Good afternoon, Korea. Very happy to be here. Of course, would be nice to meet you personally, but anyway. So today I would like to share with you some consideration about 2020, about the market, how WinGD was positioned in this market, and then I would like to conclude with the forecast of 2021. So let's get started. First of all, about overview of the market in last years. If you see the blue graph, the blue bar, basically it was how the market, the total market for low-speed engine developed. And you see that last year, 2020 and 2019 was the market volume was always the same, almost the same, 10,000 megawatt. And WinGD was able to reach 36% market share. But of course, this is a market volume that typically is quite low. We are in the bottom of the cycle. Typically, the market has higher volume. But anyway, what is remarkable that the WinGD market share increased, and this also thanks to Korea, where basically is our most important customer. I will show you in the latest slide. About the ship, the market was the tanker market was quite strong. Many VLCC was contracted. The market was relatively weak, but anyway, as expected. The container segment, especially toward the end of the year for the 15,000 plus and also the 12,000, 30,000 was strong recovery. And also we are seeing this year that is a segment that has a lot of activities. LNG carrier was as expected, so a good market, a strong market. So overall, the expectation of 2020 was actually also better than the forecast, but still the market is relatively low. We expect for 2021 and market recovery. A little bit about WinGD, what we sell more. We sold last year 152 engines. 111 are XDF, and the rest are diesel engine. So XDF for WinGD represent almost 60% of our contracted volume. Our best selling is 72DF, especially for LNG carrier. But last year also we had 92B for container and some 62DF for some other ships, no LNG carrier. So that is to give a little bit the hints about the portfolio where we sell more. Now, what is very important to remark here today that our most important customer are courier shipyard and engine builder. The first two shipyard are Hyundai and Samsung. The first two engine builder are Hyundai and HSD. And that is very important to remark. WinGD believe that Korea is still our strong market. We have a very strong team in Korea. We want to continue the collaboration in the Korean market. So that is very important to remark. Our relationship with Korea is for us very, very critical and strategical. Now, let's see a little bit the market in several countries. Globally, WinGD reached the 36% market share. In China, we achieved 40% market share. I would say that the market last year was split between China and Korea. China had almost 5,000 megawatt, Korea 4,400. In Korea, we reached 30% market share, a little bit less compared to 2019, but still, as I showed you before, Korea represents for WinGD the first customer. And in Japan, the market is a little bit lower, is only 384 megawatt, and WinGD has still a good presence there. For WinGD is very important the dual fuel market, the LNG powered ship that last year was very strong. 27% of the order intake are LNG fueled ships. So that's demonstrate that LNG is the bridging fuel, the market share increase. The share of LNG powered and fueled ships increase more and more. If we look at this 2,700 megawatt, almost 42% are LNG carrier, but 58% are no LNG carrier. That is very important sign. WinGD has a 60% of market share for LNG fueled ships, so that is also remarkable. For diesel engine, we have 26% market share, but there is also some improvement in our diesel part, especially because of the latest engine that we have developed. Now, to conclude 2021, what we expect, the market will recover. According to the market analysts, the total market will recover to about 30%. The segment that will have a good recovery are container ship. We see a lot of activities already at the beginning of the year. Many orders are in discussions. LNG carrier, we expect also there an increase of about 20-25%. So more ship will be ordered. Also, we see a lot of projects that are in discussion. The bulker will have the big jump. We expect that the market will almost double, more or less. The tanker, there are signs also there of recovery. So that's from my side. I would like to thank you. I would like to remark that WinGD want to continue the collaboration with the shipyard in Korea. We believe that is very strategical for us, and we have in discussion a lot of project, the introduction of the XDF 2.0 with the major yard. We believe in the strong support yard engine builder. So thank you very much from my side, and back to you. Estelle, do you?
Thank you very much, Roberto. And also the next topics will be continue and by George. Yes, George.
Good afternoon to everyone in Korea. Thank you for joining. And welcome to the presentation about the XDF 2.0 technology and ICER, which is the intelligent control by exhaust gas recycling. So the ICER technology, what it mainly achieves, it reduces the charge reactivity by substituting part of the oxygen with cooled exhaust gases. This allows better control of the combustion, which enables an increase in the compression ratio and ultimately an increase in the thermal efficiency. ICER improves the thermodynamic behavior of the XDF engine in terms of gas consumption, of firing pressure fluctuation, and emissions. The ICER consists of a low pressure exhaust recycling path, including an efficient exhaust gas cooler with neglectable contamination of cooling water due to clean gas, fuel, and combustion. This is a layout of the system. So when we look at the system, the exhaust gases after the turbocharger are split. There's one path going into the funnel and one path going into the ICER line. A back pressure valve is right after the split is controlling the amount of exhaust gas that is being recycled. The exhaust gases are channeled back to the exhaust gas cooler, which cools down the exhaust gases before they enter through a shutoff valve or through a flow regulating valve at the turbocharger inlet. Another shutoff valve right after the T-split is also included when the system is shut off to isolate the ICER line. The exhaust gases are cooled using fresh water. The fresh water goes through a circulation tank. There's a pump which constantly circulates the water and cools it through a plate heat exchanger. There is also a purging function that will be implemented in the system to allow purging, cleaning of the pipes when ICER is shut down. Moving on, the benefits of the ICER are reduced fuel gas consumption. In addition, we have a reduced liquid fuel consumption when operating the DF engine in diesel mode, which is a result of the increased compression ratio, which is achieved by installing the technology on the XDF engines. And of course, last but not least, we have a reduction in the methane slip of up to 50%, which is a result of the allowing the exhaust gases to burn once again in the cycle by recycling. If we look at the improvements in the gas and diesel fuel consumption, we've taken as an example for a typical LNGC vessel, the typical CMCRs for such LNGCs with 5X72DF. And we look at the graph, you can see that on the left-hand side, the improvements between the XDF and the XDF 2.0. So we're going from improvements from between 4 and 6 grams, and the lower loads, of course, the improvement in gas consumption is better. Better improvement is a result of the firing pressures that are achievable, because at the high loads, we are limited by the max firing pressure from the engine structure. Similarly, you see the improvements when comparing to the XDF, standard XDF engines in diesel mode. The emission improvements are shown. We have, in addition to the lowering of the CO2 equivalent as a result of the reduction of the methane slip, we also have, compared to original XDF, also a reduction of the, an improvement in the NOx emissions, a lowering of the NOx emissions, which is a result of the lower temperatures achieved in the combustion chamber, again, resulting from the use of the exhaust gas recycling. Particulate matter remains, of course, on the same low level as original XDF engines. Here's an example of the proposed arrangements on a 5X72DF 2.1. The engine is placed, the ICER equipment is placed as close to the engine as possible. This ensures that we can have minimum adaptations to the vessel design, use up the minimum space in the engine room. And this, of course, arrangement is possible on other vessel types as well, depending again on the engine room designs. Some information, just an overview about the differences between a standard X72DF and a X72DF 2.1 with the ICER technology. The engines with the ICER technology, in case X72 is 5 to 7 cylinders, 5 to 7 cylinders at the moment, because we first have released the single turbocharger executions. Other differences compared to the base design to an original X72DF include the small optimization on the bed plate, new bed plate with flexible main bearing girders. Most important change is a new control system, moving to the WISE control system instead of UNIC. The supply unit is the same. The fuel gas supply system can be GVU or our IGPR. ICAT system is optional. And then there's the ICER related updates, which are some changes, a new design group on the engine side at the turbocharger inlet. And then in the engine room, mainly there's the space reservation required for the ICER equipment and some changes to the MIDS related items for water system, for the cooling water system, exhaust gas system, and leakage collection system. Some information about the estimated bleed off water amount. The recirculated exhaust gases are cooled down to below the dew point, 42 degrees Celsius. So water condenses out of the exhaust gases, and bleed off water is positive most of the time. The final, the amount of bleed water will depend on the ambient conditions, and this you can see in the graph to the left. Regarding the condition of the bleed off water, we've tested after many hours of testing on our test engines, RT and RTX5 so far in Trieste. The bleed off water has always been within the requirements of the Annex 3 resolution of MEPC, so always within 15 ppm oil and water limit. It was considerably below that, so it's not an issue for discharging it. And also the pH levels were within acceptable levels. If we move on to technical details of the system, on this graph, the figure illustrates the optimal operating window of the existing XDF engines. To the right, the mixture becomes too lean and increases the combustion instability. To the left, you see that the rich limit indicates the point where the mixture is becoming too rich, so there's low air to fuel ratio, and this leads to higher combustion speed and possible auto ignition. There is no immediate gas trip when crossing a limit, since the firing pressure, knocking or misfiring are constantly monitored, and the air to fuel mixture is controlled by a wastegate. So this is the auto combustion cycle combustion principles as you know them on the XDF engine. So with the ICER technology, we can improve the combustion stability. So on the x-axis, we show the gas reactivity, which depends on the exhaust gas recycling rate and the air to fuel ratio. The reduction of the pre-mixed gas reactivity leads to an increase in the ignition delay and slower combustion speed. increased resistance to the auto ignition and the reduced combustion speed enable control of the combustion phasing even at higher loads, and a reduction of the firing pressure to stay within limits. So this allows ultimately an increase in the geometric compression ratio and constantly an increase in the thermal efficiency in both gas and diesel mode operation. And of course, we have a reduced sensitivity to the ambient conditions. What are the effects? What is the influence of the exhaust recycling on the actual gas composition itself? We see in these two graphs typical example at 75% load on the left. You can see the composition of the exhaust gases as the exhaust gas recycling rate increases, and to the right at about 50% exhaust gas recycling, what is the typical composition? So the inert gas content is increased, as you can see, by about 10%. The effect of the increase of CO2, which has a higher capacity compared to oxygen, leads to reduced peak temperatures in the combustion chamber. In addition, the decrease of the oxygen, as you see, oxygen is decreased by about 10%. In the scavenger results in reduced premix gas reactivity and a slower combustion speed, and therefore lower peak temperatures. Therefore, increasing the exhaust gas recycling rate has a positive effect on the ignition delay and therefore smoother combustion. Moving on to the performance improvements with the system to provide a few more details. So you can see the effect on the actual gas combustion on the left. The left graph shows the effect of actually increasing the exhaust recycling rate. So as we increase the recycling rate, so each curve going downwards represents an increase in the exhaust recycling rate. So as you can see by the shape of the curve, the combustion becomes smoother. Of course, if the recycling rate is increased too much, the fuel consumption will increase. So therefore, the optimal recycling rate is chosen to give an optimal combustion behavior and improved fuel consumption. This is achieved in combination of controlling the pilot injection timing, which is shown on the right. The effect of controlling the pilot injection timing shows that, for example, when we delay pilot injection by a few degrees, but the EGR rate is maintained the same. So in this case, we're showing the graphs indicate at a constant EGR rate, what is the effect of delaying the injection timing. We see that we can control the combustion by means of diesel pilot fuel injection to provide optimal efficiency. So ultimately, the conclusion is by controlling the recycling rate and with the control of the pilot injection timing, we can always control the combustion. We have optimal controllability of combustion to optimize over the entire load range. The fuel consumption benefits, we showed some figures before, but here again, based on the results that we've done from multiple tests, the increase, the left graph shows the increase of the thermal efficiency by increasing the compression ratio. So each graph represents, as we move downwards, a higher compression ratio. As I had mentioned before, at higher loads, the efficiency gain is slightly lower compared to lower engine loads because we're limited by the max cylinder pressure allowed by the engine structure. And the right-hand side is depicting the similar effect by increasing the compression ratio. Very important, as mentioned before, is the decrease of the methane slip, which results in an overall improvement or reduction of the GHG emission footprint, which for the XDFD engines with the ICER system. The reduction is approximately 8% with a target compression ratio. The graphs simply show this reduction in overall GHG emissions by choosing an increasing compression ratio. The blue shows the standard current compression ratio used on XDF engines without the ICER, And as we move to the right, this is increasing the compression ratio and showing the effect on the overall CO2 equivalent emissions. And again, with our target compression ratio, we based on our test results, we are achieving approximately an 8% reduction. Moving on to engine operation. Engines with the ICER technology will have essentially basically three modes of operation. We will have gas mode operation, of course, diesel mode operation, and third mode of operation is called the combustion stability mode. The operation in gas mode, we should point out, with the ICER technology is always without DCC over the entire load range. The fuel sharing mode is a fourth mode, and this is only an optional mode and must be requested separately. Moving on to the details of each mode, this is all the information that's been included and described in detail in our marine installation manual. The diesel mode is remains unchanged, and of course the gas mode operation as well. The new mode we have is the combustion stability mode, and I would like to provide a few more details about that on the next slide. So the purpose of this combustion stability mode is to have a stable engine operation in case ICER is not working. So if the engine needs to continue operation on gas, but the ICER equipment has malfunctioned or there's issues with the control system of ICER, then continued operation in gas mode is ensured over the entire load range, even without ICER in this mode. This can be active at as low as 26% power. And of course, the control system, the engine control system, always is controlled or handling the ratio. So the ratio between gas and fuel injected, liquid fuel injected at higher loads is controlled by the engine control system to ensure always stable operation. With the CSM mode, when active, the engine is always Tier 2 compliant. And finally, some information about the ancillary systems. This is all information also included in the MIDS, in the Marine Installation Data System drawings, which are linked to the recently released MIMS. The changes are mainly to the cooling water system and the exhaust gas system. The cooling water system, you see here on the right, depicts how the system is laid out. And so, as I mentioned, there's an exhaust gas cooler circulating pump, which circulates the water from the circulation tank through the plate heat exchangers, which cool this fresh water, and which is used then to cool down the exhaust gases in the exhaust gas cooler, and then continuously going back to the circulation tank to complete the cycle. The freshwater level in the system is kept by a level switch and a solenoid valve. So in case there's excessive water, this is in the circulation tank, this is automatically let off. And finally, on the exhaust gas system, in this picture, which is also contained in our MIM and marine installation data systems, there's important changes to the exhaust gas system. As you can see, presented in the first slides, after the after the turbocharger, the exhaust gas, part of the exhaust gas is bypassed into the ICER line. Here's the back pressure valve, and here's the shutoff valve. The exhaust gases that are recycled go back through the exhaust gas cooler and into the turbocharger inlet. We do foresee at the TC inlet, this will be part of the engine group design. So from the flow regulating valve downwards and to the turbocharger inlet, the housing, the connection piece, and a water trap we foresee will be an engine group. So will be part of the engine scope of supply. So placing the ICER, again, as mentioned before, close to the engine requires, of course, no blower and has a number of advantages. First being a faster response on the exhaust gas rate to the engine, then the no risk of condensation in the duct due to lower temperatures and better fuel consumption. due to improved characteristics. Thank you very much. I would like to hand over now to Adrian.
Well, thank you, George. 안녕하세요. Good afternoon, everybody. 반갑습니다. I will have the pleasure to introduce you our brand new 72DF engine, the upgraded version. They were shortly touched by and Kim earlier and George, and we will dive now a little bit into the details. My name is Adrian Siegfried. I took care of product management before, now leading our new customer support team in WinGD, Switzerland. So, in a nutshell, yeah, I apologize. That's a lot of text. Why are we doing this? Why do we upgrade the well-established 72DF? As a matter of fact, we had this in mind for a longer time, and we want to beef up the engine with the latest technology, which is meanwhile available, such as the WISE control system. The rollout into the portfolio started, and now with the 72DF, with the 1.1, 1.2, 2.1, 2.2 versions, these will also be taken in. The wide, of course, this we have. The DCM unit comes significantly simpler along with the WISE control system. Less modules are needed. So this is a logical consequence. We have a strong focus on optimizing the production cost by various measures. We will look at this a little bit later. Basically, we want to implement validated designs, so nothing new, but the technologies which were validated on other engines. So to minimize say the surprises, we would like to launch a product which is as good as it can be from the very beginning. Finally, also we implement some let's say findings from the field service experience. We have seen not everything runs perfect, and now better solutions will be taken in account from the beginning. Finally, then, yes, we do have, of course, still our XDF low pressure technology in the Otto cycle, very competitive in the respect of the CAPEX, OPEX as well. And as mentioned, yes, we do have the interface readiness for the ICER technology. And the target market, yeah, we can say, or we can argue that the 5X72DF engine was very successful for the LNG carrier market in the recent past. But we also would like to extend a little bit the applicability to other ship types as like tankers, bulk carriers, container vessels, let's say ships in this mid-segment where the new 72DF engine can present a drop-in solution. A drop-in solution in respect that not much has to be changed on the engine side, engine room side, apologies. So the new engine should fit widely into existing ship designs based on an old, so-called old 72DF engine. Looking a little bit more into the segmentation, we do have the 72DF 1.1 engine at the bottom, at the top left. This is applicable as 5 to 8 cylinder engines for higher powered vessels, containers, tankers, bulkers. They will profit from the upgraded engine design. Then we have the 72DF 1.2, applicable only as 5 and 6 cylinder engine with a reduced rating field. This is targeting, let's say, the standard LNG carriers as we see them today. We do have also then the 2.1 version, again, applicable as 5 to 8 cylinder engine with the ICER applied, and the 72DF 2.2 at the bottom as 5 and 6 cylinder engine execution with ICER. And when we look now into our engine portfolio, the rating field on the right-hand side, the new 72DF engines are highlighted in this light gray. And we can actually see that we have this smaller rating field for the 72DF 1.2 and the 2.2 engines. And that is also reflected in the left-hand side. Because obviously the R1 rating, the R1 point, and also the max power output of these 0.2 engines will be changed a little bit. So the 1.1, the 2.1 will actually keep the R1 rating as we have it today on the 72DF engine at 89 RPM, while for the 0.2 engines, we go down to 79 RPM. For the MEP, the mean effective pressure, this means we are reducing the upper line from 17.3 bar as we have it today down to 15.7 bar. Cylinder configuration I mentioned, the 0.2 engines will be applicable as 5 to 6 cylinder, and this will allow quite some benefits on the engine structure side. Here, once again, a little bit, let's say, stretched apart. On the left-hand side, we do have the 1.1 and the 2.1, the whole rating field, which has the same coverage as the today's 72DF. And the smaller marked area out of that, this will be then the 0.2, the 1.2 and the 2.2 engine reduced R1, R2, R3 points, R4 will remain the same. And along with this one, also a reduced maximum power output and reduced MEP. So, and here we have it a little bit simplified. I hope it is simplified or easier to understand. Engine details, what do they look like, or what will they look like? On the left-hand side, we have the 72DF, the 1.1 engine, applicable as 5 to 8 cylinder engine. With the flexible girders, this is some, let's say, weight optimization on the bed plate, which is meanwhile validated. We have it introduced on the 92DF, on the 92B engine, and now the 72DF 1.1 will be the next one. The crankshaft, this will be a FCV4 standard execution, as is already available since last year. Subject, of course, to torsional vibration calculations, but this is available technology. The engine control system will be the WISE, the next level we have now. And the supply unit, yeah, we stay with the standard supply unit on the engine as we have it today, with 2 or 3 fuel pumps of the big size. The 1.2 engine on the other side, 5 to 6 cylinder, will become a little bit shorter. We do have a shortened bed plate. And this is feasible because we apply a smaller supply unit. We were in the lucky position that the newly developed supply unit for the X72S engine also fits on these smaller rated 72DF engines. So this small supply unit, in conjunction with a shortened thrust section, will lead to a shorter bed plate by roughly 300 millimeters. And this is representing a major cost down on the bed plate side, but also on the crankshaft side, which is, let's say, beneficial for sure to make the engine more competitive. I mentioned the crankshaft, along with that it's getting shorter. We can also make it lighter because we have less torque to transmit. And of course, the WISE control system remains there, same as for the 1.1 engine. And now the change to the ICER engines, the 2.1 and the 2.2, is in principle not so much. It was mentioned that at present the ICER technology is available only for a 1 turbocharger application. Thereby, the X72DF 2.1 will be available for time being with 5 to 7 cylinder engine configuration. The 2.2, this is again 5 and 6 cylinder with a shorter bed plate, with a small supply unit, the slimmer crankshaft, and so forth. A brief overview. Yes, we are combining existing technologies into a bundle and apply this on this engine upgrade. Bed plate, this is existing from the 92DF concept of the flexi girder. We are currently also looking into the optimization potential for the cross head. There seems to be something feasible. Piston crown, at the moment, we have seen that the 52DF engines, the first application with touring piston crown, in the field operate very well. So this we will also implement as a, let's say, a cost optimization feature for operators mainly. The piston, the cylinder cover will remain widely the same, although we will implement a change on the pre-chamber to make the pre-chamber sealing a bit better. The rail unit box on top left side will be adapted from the 72B engine, which already has the WISE control system. On the cylinder liner, we actually stay with the 72DF with a uniflow cooling system as we have today, although the port height will be adapted for ICER and higher compression ratio. And the crankshaft, these are already mentioned as a FCV5 execution, subject to TVC allowance, representing a cost optimization. in a different view now. Engine management, top left side. Yes, we have the WISE. I mentioned the rail unit box from the 72B will be adapted. The Conrod crosshead guide shoes, we are looking into some weight optimization there. This looks actually quite positive meantime. Then drop-in solution, the 62S supply unit, more compact, using the smaller size fuel pumps as we have them on the RTFlex 50 engines today with a very good track record. Bed plate girders, this was mentioned. We move to the more flexible girders, lighter girders. We also implemented this opportunity, a new foundation bolt concept, basically downsizing the bolting. Shorter truss bearing section, I talked about that. Then we move to the right side bottom, the shorter crankshaft, lighter execution of the FCV5. Scavenging, of course, the scavenging group will need adaptations to not only the ICER, but also this is now a chance to introduce the new cooler generation. Finally, on the 72B engine, the C-type cooler. Then piping platforms, they will undergo some optimizations, adaptations, of course. Also reinforcements may be needed for the ICER. We will also implement the air separator onto the engine structure again. And on the hot parts, we increase slightly the compression ratio. We will implement a new pre-chamber design with better sealing capability, and piston ring design will be updated. Piston ring and piston crown design will be updated to the latest standards. Yes, this is more or less the same, I would say. We stay, of course, with our flex control system, with the flex control in respect of a servo oil, high pressure system, 300 bar. The cylinder lubrication system, this will be now finally the Flex Loop Mark E, our latest pump design, which is more accurate and which should also bring the production cost down over time. Local combustion chamber components, no change in that. Fuel pumps, depending on engine rating. This is then relevant for the 1.1 engines. Okay, the WISE control system. Yes, maybe to mention, we intend to stay with the fast injectors as we have it today from L'Orange Woodward. Meantime, the track record has improved quite significantly. We have seen service feedback. The crosshead lubricating system will keep the high pressure pump as today. Crankpin bearing, we stay with the aluminum coating. We have seen this is actually working very, very well in operation. Not a single fail till date, so very good track record. The footprint will change a little bit for the 0.2 versions, but let's say only in respect of engine length. So the width and the height and so on of the engine remains the same. And finally, yes, we will have both IGPR and GVO solution if somebody is interested in that, which are fitting for the new 72DF engine. Project timeline, a few words on that. We do have pilot projects in the focus in Q1 2022. 1 year from now would be bedding roughly. And we are now working hard to get the drawings ready in time. The TIN, the official announcement of the engine to the market, has been released just recently. This is available on our homepage, and WinGD also actually released or announced with a press release last week that the new engine is coming. And with this one, I'm at the end of my presentation. Thank you very much for your attention. Kamsahamnida. And I have the pleasure now to hand over the word to Dominik Schneider. Dominik, the floor is yours.
Yes, good afternoon, Korea, and hello from the morning in Switzerland. I have the pleasure to discuss perspective on alternative fuels, as we call it here. My name is Dominik Schneider. I'm the responsible Vice President R&D in WinGD. So today I will show you the latest publications on the subject. A lot is going on, a lot is being discussed. Then a few technical considerations related to green fuel, regulatory considerations. Then the reference to our XDF platform, which was already introduced by my colleagues again. And then an outlook on our future fuel matrix. To start with the latest publication, I always like to show the DNV Maritime Forecast study. It was published in September 2020, so it's again 6 months old. But what I like here is particularly their approach with looking at the regulatory ambitions. So they clearly look at legislations to start with. They look at fuel price, potential fuel price development, and then also seaborne trade scenarios. So they really have a scenario thinking. And in the last study, they actually kind of highlighted 2 scenarios. One was a slow but steady shift towards ammonia, as you can see on the top center. Another one was a slow but steady shift to methanol as fuel. Now, the difference between the 2 fuels, ammonia is NH3, so carbon-free, while methanol has still carbon in it, but it's considered carbon neutral. On the top, you see also that the DF engines are the base for the transition, and that the monofuel internal combustion engine, as they call it, is probably not the right future. You can also see that in the bottom graph, where you see at the bottom in red, actually the current oil-based fuels, liquid fuels. Then in gray, you see actually the LNG, the natural gas fuels, and in the kind of rosa, then actually the low carbon fuels coming in. On the timeline between 20 and 2030, excuse me, we will see that actually LNG or natural gas is the bridge over troubled waters before low carbon or carbon neutral fuels are coming in later on. Related to LNG, another interesting publication just at the IMO Symposium 2 weeks ago, Xavier Leclerc from CMA was showing this slide, and actually he showed what is already possible at current technology. The 23,000 TEU container vessel of CMA, or X72DF, and they made a study for this particular vessel based on measurements, a comparison between emissions of diesel-like fuel, so low sulfur fuel, versus LNG as fuel. You see on the top the consumption figures, and on the bottom you see the emissions. So related to greenhouse gas emission, it's obvious that the CO2 footprint was reduced almost by 25%. And again, this is based on measurements and not prediction. But even more astonishing is that the pollutants like sulfur oxides reduced 99% confirmed, NOx confirmed minus 92%, and particulate matters minus 66%. So very, very impressive figures, and for sure the right step to go for ship owners that are considerate and want to make a mark related to environmental protection, reducing their emission footprint. And this technology is available right now, and we don't have to wait for future developments. Another impressive announcement was the one last week by AP Møller Maersk. Sure you have seen that. They made a press release that they will have the world's first carbon neutral liner in operation by 2023. You had to read through the text to see that they actually count on methanol as fuel. Again, methanol is carbon neutral. And I mean, the main decision in the background is actually that also now AP Møller starts to invest in dual fuel engines. So far, they have refrained from that, and now they act, and they will start to order the first dual fuel vessels. Here, 2,000 TEU is highlighted very clearly for regional deployment, where the methanol is available in sufficient amount. It's not yet the fuel available on a global scale. Nevertheless, also this is an important step in the right direction, and it clearly shows that the high flexibility from the technology provider is needed. Some considerations on the fuels here. The graphs are actually originating from a WinGD internal studies addressing the whole variety of fuels available and benchmarking them with a reference fuel. The reference fuel is always MGO, which is available sufficient amount to the industry. Now, if you look at the different fuel, here we see hydrogen, ammonia, methanol, and methane. Technology readiness level shows that actually hydrogen is basically commercially available from renewable sources of electrolysis mainly. You can see in the darker blue, the bar graph goes up to level 9, 10 is maximum, that's MGO, the reference. So hydrogen is available. While methanol and methane become commercially available, you see methanol and methane at the very right, they are becoming available, but not in sufficient amounts yet, and very low amounts. Project investments are mainly going into hydrogen and methanol. You see here the APM Maersk investment in methanol, CH3OH, or Yara is investing heavily in ammonia. Those are just example. More investments are done in global scale. Fuels are becoming available. Technology is development. Now, related to production volumes, it's clear that hydrogen is leading, but it covers currently, renewable hydrogen is currently covering only 3.4% of the global demand in shipping. So it's still very far for being available in high amounts. Then ammonia coming in second is only 0.15%. So huge investments need to be done in the infrastructure to make renewable fuels available. And these investments will take a few years. They're all lined up again and again. You read news that this infrastructure is being built and becoming available, but until the fuel is being available, that's several years down the line. Therefore, likely also the APM decision only to go for 2000 TU to start with for regional deployment. Another perspective on these fuels is related to production cost, and clearly say production cost. That's not the value in the market because there might be some incentives, and process efficiency. Also here, this is always compared to MGO as reference fuel. In a nutshell, we can say that that's actually hydrogen and methane have the highest average upper boundary efficiency. What that means, to produce hydrogen and methane needs the least energy compared to the other fuels, the other renewable fuels listed here. So ammonia, for example, or methanol need more energy to produce than hydrogen or methane. In the base benchmarking here, the carbon dioxide origin is not accounted for. So if it's, for example, coming from an extensive carbon capture program to reduce carbon in the atmosphere, then of course the efficiency would be further decreasing for methane and methanol and methane. The production costs, hydrogen and ammonia are the most feasible. You can see that they come actually about factor 3 compared to MGO. If you look at the graph, while methanol and methane show the biggest range. So while the average is rather high for methane, for example, at almost 5 times of MGO or even more, the range is very huge. Also here, it depends on the source, the feedstock of the methane. Is it biomass feedstock? Is it electrolysis and methanization as showed here? That makes a big difference. And also incentives from regulators, tax levies, etc. could benefit the fuel price. So this also showed that actually local tax effect on the availability and cost of such fuels. For example, in the Netherlands, such fuels are incentivized by the governments, and fuel is available at rather low cost. So local ship operators are of course very interested to use these fuels. Here a bit of a complicated table. What I want to show here is actually some highlights. On the left, in the first column, you see parameters which are important for us as an engine technology provider. We need to understand the fuel, and then we compare all the fuels amongst each other, benchmark amongst each other. But you can see here that, for example, hydrogen, it's known minus 253 degrees boiling point, so storage is a challenge. But then also the lower heating value, the energy we put into the engine with the fuel, for example, for methanol, ammonia, is 60% lower compared to methane, while hydrogen is 140% higher. So the volumes differ quite considerably. And if you prepare now an engine for several fuels, like for example, a 3-fuel engines, you need to consider that. It's quite a challenge. Another important parameter is the outer ignition temperature of the fuel. Here you can see that the alcohol, methanol and ethanol, have a disadvantage. They ignite quite early at low temperature. That means that the Otto cycle is actually not really an option for these fuels because there might be early ignitions. Another important factor is actually what is the ignition energy needed to ignite the fuel for the combustion. Here I would like to highlight ammonia. Ammonia needs 680 times the energy to ignite compared to methane. So that's definitely a challenge for an engine developer. Another challenge also related to ammonia is the laminar flame speed, how fast burns the fuel. You see, compared to methane, it's 80% lower. That means probably the slow speed 2-stroke engine with the long cycle time is the only engine that can accommodate ammonia, pure ammonia. Other engines, they will need a catalyst to increase the flame speed. And also here, the volume specific heating value, again, I mentioned before, depends really on the fuel. All this fuel needs more volume. You need to inject more volume per cycle. You need to have bigger storage capacity on board. Then the regulatory considerations. Of course, the regulators, they have mainly a focus on emissions. The safety standards become available. Just recently, DNV-GL or DNV now released the very first draft document related to ammonia, so some standards become available. But what remains unclear is the gases emission regulation, and here particularly the greenhouse gas and the global warming potential of the fuel. We had just had EXI and CII introduced. The road forward is a bit unclear. The EEDI phase 4 is being discussed. But here the global warming potential considerations of various gases needs to be clarified. For example, black carbon is a big discussion at IMO. CH4, the methane slip, is unclear. Will it be added or not? NOx has a greenhouse gas potential. How will that be accounted for? N2O, particularly addressing ammonia as fuel, NTO becomes an issue. How to address this with the global warming potential? And then not to neglect it, even nobody likes the idea, we also have to account somehow the CO2 emissions from neutral fuels. Even the fuel base is CO2 neutral, so the CO2 is retrieved from the atmosphere when the plants grow, for example. In the combustion, after the combustion in the engine, CO2 is emitted and goes back into the atmosphere, and how to account this for needs to be clarified. And this is only addressing the greenhouse gases, which have higher public focus now, but we cannot neglect all the pollutant emissions like further NOx regulations. The EC, for example, addresses that. Regional regulations in Germany, Italy, for example, they're very stringent. There's no chance to come in with a marine classified engine in these areas. Additional measures are needed. The same is valid for particulate matters, PMs. Sulfur oxide, and coming new into the picture, formaldehyde. So all this needs to be clarified. So this unclear regulation roadmap and also the unclear availability of fuel needs actually high flexibility from technology provider and also on the retrofitability of the installed. To bridge over to the XDF platform and how we see the answer to this challenge actually. Here on the picture, you see on the right side actually the various fuels. You could add a couple more here. An example, these fuels fundamentally, most of this fuel can be burned either in a diesel cycle or a lean burning Otto cycle. So our XDF engine in our view is actually the perfect platform to accommodate this fuel. And wherever regulation goes, we are able to flexibly adjust our technology the best way. So in other words, if you have the XDF installed in installation, you have no dead end looking forward. So you can retrofit whatever is needed where the regulation goes or the fuel becomes available. A bit more specific, the diesel technology obviously is better for efficiency, therefore CO2 reduction and CO2 equivalent reduction because of the maximum combustion efficiency. It has disadvantages on NOx as long low sulfur fuel is used also on SOx and on PM. The diffusion cycle is critical for particulate matters. And if you would use ammonia as fuel in this cycle, N2O will become a clear issue from the combustion, but then also from the SCR after treatment, where we will have laughing gas as a result, needs to be addressed here. The Otto technology, due to the low combustion temperature, is very beneficial for NOx. Due to low pilot volumes, SOx, pilots could be also sulfur-free when they come from a biomass feedstock, for example. Particulates and N2O is also expected to be lower, but with certain fuel slips, particularly in methane as fuel, we do have CO2 control required. The ICER system was just introduced. Further technology steps will be needed and are also planned. So looking forward at all the fuels, we have all built such a matrix, how we see the retrofitability of the fuel or the applicability of the fuel. In the left column, you see the various fuels, starting with the low sulfur fuel oil, HFO still available, of course, the base of fossil, biodiesel. Of course, the X engine here is the perfect base. The X engine is optimized for such diesel-like fuels. It's really engineered, tailor-made for diesel fuels, including HFO, so the best solution for such fuels. The modern X engines, they have the same engine base as the XDF, so actually any of the modern X engines, they can be retrofitted for Otto cycle combustion as well, so LNG, biomethane, synthetic methane combustion. They could also be retrofitted logically for an ammonia application or a methanol-ethanol application. Hydrogen, we do not really see as a pure fuel on a two-stroke engine because the combustion speed and the ignition, it would be a very fast combustion. Some people talk about almost an explosion. So here we see hydrogen at the maximum as a blend in, a mixed in, or we have to introduce measures to reduce the flame speeds. Now the XDF engine, again, is based on the X engine, but has additional features. So anything related to methane is already implemented by design. Looking forward, we see clearly also the retrofit ability of ammonia or methanol feasible. And actually, some of these retrofits are not even a big effort because the technology is available. Fundamental research has been done with some of the fuels. And it's just a matter of rolling out or making these solutions available to the market on the portfolio. With that, I close my section. Thank you very much for your attention. And I think I will hand over to Rudi Wettstein. Yes.
Good afternoon, ladies and gentlemen. My name is Rudolf Wettstein, and I'm in charge of application engineering. Today I have the opportunity to introduce the new 52 and 62 bore short stroke engines, which will be available in the diesel and dual fuel technology. These new short stroke engines are introduced for the market of container feeder vessels, multi-purpose vessels, car and truck carriers, Ro-Ro and Con-Ro vessels. So ships with limited main deck, limited design draft, and thus also limited propeller diameter. To transfer the required thrust, they need higher RPM on the propeller. And for this reason, higher RPM actually calls for shorter strokes. These two new engines are also replacing the successful RTA RTFlex 58 bore engines. A total of about 750 engines have been built and delivered during the last 20 years. These engines are now reaching the end of the lifespan. The 5262 long-stroke engines, they remain in the portfolio, and they are specifically designed for tankers and bulkers with lower shaft speed requirements. Here we can see the rating field of the 62 bore engines. Dark blue, the short stroke engine in the speed range of 85 to 108 RPM, and the long stroke with RPM down to 77. You can see also the RTFlex 58 TD rating field, which was going from 84 RPM to 105. So it means the new X62 short stroke is in the same speed range. Adding then the 52 short stroke engine below with 95 to 120 RPM speed range, you can also see there the long stroke 52 with RPM down to 79. The dotted line again, RTFlex 50D, in a speed range of 95 to 124. Here we have slightly shortened the rating field, and so it is now a good coverage for the mentioned ship types. So we can call the short stroke engines the container feeder and PCTC engine, and the engines which go into the lower RPM range, the typical tanker and bulker engines. Of course, there will be overlap. You can see also the rating fields are overlapping. So ship designers have really here a choice to select one or the other engine if their project calls for a specific engine power and shaft speed. We can see here the parameters of the short stroke and the long stroke engines. If we look to the stroke, we see that the short stroke is roughly 400 millimeter shorter, leads then to the shorter stroke to bore ratio. Cylinder numbers are identical. Power output is somewhat lower for the short stroke engine because of the shorter stroke. This results in a lower cylinder power. Speed range I mentioned already, and mean effective pressure is raised from 21 to 22 bar. Together with an increase in firing pressure, this will give us a 4 grams per kilowatt hour lower consumption. Gas consumption is forecasted to be equal. On a 52 bore, similar picture. Here we have around 270 millimeter shorter stroke. Cylinder power about 100 kilowatt higher because the speed range here is going up to 120 RPM. So speed is contributing to the higher power at the R1 power. Speed range I mentioned before, and here similar, mean effective pressure 22 bar, and as well consumption some 5 grams lower than the long stroke engine, mainly due to firing pressure. Coming to the dimensions, the 62B long stroke 8.1 meter, short stroke is 7.2, so this is a reduction of 850 millimeter. Bed plate is, of course, with the shorter stroke also lower. Then piston removal height, nearly 1.5 meter, 1.4 meter. So this is very good for the lower main decks. Weight is something like 14% less than on the long stroke, and this will, of course, contribute very positively to the production cost. When we compare with the competing engines as 60, we are a little bit shorter, And also here in piston removal, something like 180 millimeter lower. The 52 bore dimensions, similar picture, shorter than the long stroke, 1 meter lower piston removal compared with the S59.7 here, as well an advantage of about 0.5 meter in piston removal, also about 0.5 meter in engine length. Similar picture on the material demand components, something like 14% less total weight. When we compare the consumption with a competitor's engine, we have here 4 covering points, A1 to A4. So we have plotted the specific consumption over power on these 4 points, and to the right side you see there on the top line A1, A3, we have in the power range of about 50–60% power, we have something like 7 gram lower consumption, or around 3 grams less on the lower rated engines. So ships are mainly contracted at 90% engine power, and here you see the great advantage with these 2 new engines with around 9 grams, respectively 5 grams lower consumption than the competitor's engine. So this will, of course, dramatically reduce OPEX for operation of such a ship and makes these engines very attractive. Similar picture on the 52 bore, again the covering points A1 to A4. Here it's somewhat different because specific consumptions have been different, and also the influence on the rating field. Here we have something like 4 grams for the top rated engine and maybe 6 grams on 50% power on the lower rated engine. But again, on 90% power, something like 6 to 7 gram lower specific consumption. Component designs, we see the major design principles here. Of course, we are using a lot of concepts on previous engines. To the right side there, I can say that all upgraded and new engines get this WISE engine control system. Korean engine builders are already familiar with it because it's already in operation on the X72B engines. So it's a future-proof system with clear interfaces, modern architecture, and powerful processors. Also on the dual fuel engine, we need only 1 processor per cylinder and not 2 as on today's Unix system. Then the injectors on the diesel engine, we will have 3 fast injectors with long lifetime of 8 to 10,000 running hours. They are perfectly working on the diesel engine. However, on the dual fuel engine, we foresee non-fast because the fast are exposed to more thermal shocks, and the lifetime are not as long as the non-fast injectors. They are anyway backup fuel injectors, and with the non-fast also the OPEX maintenance costs can be reduced. Otherwise, bearing, we can still work with white metal bearing on the main bearing and crosshead bearing. Big end bearing is aluminum coated as on other engines. The smaller footprint is achieved by the reduced stroke, reduced engine height, and the reduced cylinder distance. And compactness is important. Engine room spaces get smaller and smaller. Here you can see that we have reduced the end journal on the crankshaft by 20% compared with the long stroke engines, and this results in a total length reduction of about 10%. On the bed plate, we use the same girders, these flexible girders, which will adapt better to the bearing load for a better distribution of the bearing forces. So this is what we have used already on a few engines designed earlier. The combustion chamber, designed for 5 years time between overhaul. Here I would like to mention the 2 piston ring concept. This is introduced on all mid-bore engines, 52, 62 and 72 bore engines. 2 piston rings. We have tested the 2 piston rings in the field during about a number of years on a dozen of different engines with 10,000 of running hours, and we found it really of advantage. It provides a better stability of the piston ring package, and in addition we can reduce the first cost and also maintenance costs. So 1 ring less is 30% lower maintenance cost for the overhaul of a piston. Then we have on these engines 3 liner wall temperature sensors that is the possibility to monitor the 3 injectors more carefully and can find a relation between the temperature and the working condition of the injector. Few other components. The diesel engine will have this injection control unit of the common rail system Mark III, as we use it on the RT-Flex 58 before. So this unit allows onboard maintenance for lower total cost of operation. Supply unit is in principle the same with regard to dimensions as we use on these mid-bore engines 48 to 58. We have slightly rearranged the servo oil pumps. It is a very compact arrangement, which helps us also to shorten the engine part, to shorten there the crankshaft and bed plate. And this WISE module, which is already standard on the 92 and 82, and now also on the upgraded 72 bore engines. Coming to the integrated SCR, a major development we have done the last couple of years. So it brings benefits to the shipyards. It will consume less space in the engine room than a high pressure or a low pressure off engine arrangement. It will provide savings in the installation and commissioning work by the shipyard. It is, of course, integrated into the engine structure. The control is part of the WISE engine control system. And each engine is optimized and tested together with the ICER and not just the parent engine. So that is a benefit for the engine as such, as it gets a top optimization. The design is done to run with gas oil, as the NECA is always SECA. So that is, I think, justified for an ICER, which is running a minor share of the operation time of the engine. Here we see main components: green, the catalytic elements. Then we have flow control valves. We have the urea injection and dosing system. Urea injection is just after the cylinders, before the exhaust gas gets into the receiver here. So we have to find a position for a good distribution and mixing of the urea with the exhaust gas. Then there is, of course, also a soot blowing system there, an air supply system. So this is the arrangement of the prototype engine, which will be testing during next month on a 6X52 bore engine. In Winterthur, we have, of course, already during last year tested the ICER on our test engine. here we see the flow concept, tier 2. We bypass the green catalytic elements. We collect the exhaust gas and bring it to the turbocharger. In tier 3 mode, we will open certain flaps and push the exhaust gas through the catalytic elements. We inject the urea, and we have this transformation of the harmful to non-harmful exhaust gas. We have evaluated a number of ICER concepts. This we call the mailbox design. So it is quite a demanding task in R&D to all fulfill these structural, static, and dynamic stress levels, to have a good flow analysis, to keep the pressure drop under control, and to reach a good conversion of the NOx with a very minimized urea slip. A few words about the dual fuel engine. We keep the fuel gas and pilot oil supply system as on present dual fuel engines. The only change is here we will fit an insert bush. It's a new shrink-fitted bush for the pilot injector. So this bush remains always in situ when we are removing the injector or the pre-chamber. That means we can increase and ensure the tightness. Here we have cooling water, and with this always in situ installed bush, we can definitely avoid any leakage after a replacement of the pre-chamber or the injector. We have the 2 gas admission valves per cylinder. This hydraulically operated gas admission valve, which has really proven an excellent behavior during the last 4 or 5 years in operation. So we have there the 800,000 running hours on our dual fuel engine fleet. And we have here something like time between overhaul of the valve spindle of 5 to 6 years. So it's extremely reliable, and we do actually not see a need to have 2 valves in series for safety reason. This valve is very reliable, and by the way, it's also permanently monitored. If there should be a disturbance or a failure, we have, of course, an immediate reaction on the safety system, and we insulate the gas system and trip to a diesel operation. Coming to the last slide, the summary. As you have seen, we have really best-in-class fuel oil consumption. We have reduced engine dimensions, the reduced piston removal height, very important for this type of ships. We have foreseen the engine. We are using proven design principles. We have a focus on low production costs. And as the new major steps is the ICER, which will really bring benefits to the ship designer. We have the WISE control system, also the wide engine performance and the predictive maintenance analysis system as a standard. We further try to extend time between overhauls for good operating results and low costs. And we keep the low pressure dual fuel technology on these engines as well, with low cost, low energy demanding fuel gas system. I hope you find this presentation useful. I'm convinced we have here 4 attractive engines which meet the market requirements. We have a number of interesting projects, and hope to get within the next months the first orders. Then I would like to hand over to the next presentation this will be Marcel Ott to talk about the 12X92DF dual fuel engine. Thank you very much and goodbye.
Yeah, thank you, Rudi. Good afternoon, Korea. Welcome, ladies and gentlemen. My name is Marcel Ott. I am in charge of operations Korea for WinGD. And I would like to give you an update of the operating experience we have achieved with our 12-cylinder X92DF engines in service so far. So first of all, a few of the motivations for LNG as a fuel, very general points. We assume most of you are familiar with the fact that CMA CGM had ordered 2 series of very large container vessels, 15K and 23K size with LNG as fuel. And there is, of course, a number of general reasons or motivations for that, which are listed here. First of all, environmental improvements are imminent, so within immediate effect, large achievements can be achieved, and we'll see more of that coming. Regulatory compliance is rather simple. Further reduction of greenhouse gas emissions are possible without major conversions or investments. And also commercially, it's expected to be a very attractive fuel also in the future. Technical solutions are very mature, and the global LNG infrastructure or bunkering infrastructure has been developing quickly worldwide. And I think nowadays we cannot talk about this chicken and egg situation any longer as it used to be. So the infrastructure is there and is growing further. And last but not least, of course, the LNG as a fuel gives a positive public image, and this can be seen in the example that was copied from CMA CGM's webpage here, where you see how this company presents itself as a environmentally sustainable liner operator. So to have a first look at the fleet in service, this is referring to the 23,000 TEU container vessels from CMA CGM. In fact, by now 5 ships are in service, the first of which has entered commercial operation in September last year. You see the first line in the table here, CMA CGM Jacques Sade, the flagship of this series. This ship has meanwhile accumulated around 3,000, a bit more than 3,000 running hours, and is at the moment on the return trip to Asia for the 3rd call in Asian ports. The other 4 vessels that are in service are also listed here. The last one that has entered service is CC Rivoli. This ship is on the way to Europe on the maiden voyage, still running on diesel or fuel oil at the moment, as it will bunker LNG in the port of Rotterdam. So total accumulated running hours more than 8,000 so far, and that has already given us some valuable insights into the operation of the vessels and the engines on board. For this series, 4 more vessels are going to be delivered until about mid of this year, and then are another 5 10-cylinder vessels coming until April next year. A few words on the LNG bunkering, which is of course a very specific thing on these vessels. They are equipped with large LNG tanks, 18,600 cubic meter capacity. The first bunkering has taken place in November last year in Rotterdam. You see a picture of this here with the bunker vessel alongside. During the first bunkering here, actually, 13% of the fuel that was bunkered, of the LNG that was bunkered, was renewable or bio LNG, which has helped to further reduce the greenhouse gas footprint of this vessel. Several further vessels have been bunkered. Meanwhile, 5 bunkering operations have taken place, and it's fully proven that the safety principles work, all the procedures are in place. In fact, the bunkering is done as a SIMOPS operation, so simultaneously to the cargo handling operation, so there is no loss of time for the bunkering process on these vessels. As mentioned before, the bunkering infrastructure is expanding, and meanwhile it is also possible to bunker in other ports, for example, Singapore. So a few of the technical feedbacks we can share with you of these vessels. Start with the piston running behavior of these engines, where we have seen that in service now these engines had very good piston running behavior. We have not seen issues related to this in service so far. You see that components are in good condition, as shown in the pictures here on this slide. You can also notice that there is actually very little deposits here. We see that the released cylinder lube oils, for example, do a very good job in terms of cleaning of deposits from top lands and so on. We also see, not only on these engines, but very generally on our dual fuel engines running on gas, that the piston running generally is less critical because there is no sulfur in the fuel, so there is no risk for cold corrosion, which sometimes can be a problem on, especially on scrubber engines running on high sulfur contents, but that is really an advantage here. Piston underside scrape down samples are regularly taken and analyzed. This is of course a good measure to let's say analyze the piston behavior during operation. We have seen on one unit now very recently that there is some increased iron content, so that unit is under monitoring, and we will have an inspection in the next port. But generally a very good behavior seen in service. Another issue that we have seen during operation was related to the cylinder relief valve, as we call it, which is kind of equivalent to the indicator cock on previous diesel engine designs. So here we have a sealing surface of this relief valve, a seat which is in the cylinder cover. It's shown in the cross-section picture here. And we have seen that on one unit there was a leakage of this relief valve, which has caused the valve seat and the seat in the cover to kind of torch off or burn away. And we have, or we expect the root cause for this to be an insufficient tightening in the first place, so that the leakage could start and this damage of the seat could develop over time. This was not a big issue. Actually, the biggest issue was that unfortunately the relief valve seat was not included in the spare delivery due to some mistake that was made. So eventually we also dispatched a service team with the engine maker to take care of this and replace the parts in port. So that's all fixed and back in service again. Another issue experienced is related to the exhaust valve air spring sealings. We have seen on one vessel actually that there was an increased leakage of air from the air springs, leading to exhaust valve timing failures at high engine speeds. We have also seen similar issues on some of the 92 diesel engines before, so we have actually a solution available for this with slightly modified sealing design and improved material. So this has been implemented on this vessel with good results, and is going to be rolled out for all the engines in service and due for delivery. Few words on the WISE engine control system. As mentioned by Rudolf Wettstein before, our latest generation control system that is implemented as a standard on all our new engine types. A very modern system with increased processing capabilities and fully capable of controlling also the, let's say, engines with highest cylinder numbers, dual fuel, so the highest requirements. And we have had very good experience with this system in service. Actually, no major issues faced. You see an example here of the MCP panel, as we call it, the interface panel, touchscreen, modern architecture panel, and a module that is shown here, the cylinder modules. So very good experience with this system. We have had one maybe minor issue so far, that the spare modules for the MCP modules, they need to be installed or pre-installed with the updated software, because the automatic download has not worked from beginning, but that is being fixed at the moment. I would say a rather minor issue on that. Another point we would like to highlight is about remote monitoring and our WinGD White system. I think on these vessels now we can see a real benefit with these remote monitoring capabilities that we have installed as a standard on all our new engines, and we're really exercising this now on this engine series in terms of following up on engine operation and performance. And we see that this really gives a lot of opportunities for operators, but also for WinGD to better optimize engine performance, to support for troubleshooting, support the crew in case needed, and also improve the reliability of the engines in service. So with this system, we have the possibility to remotely monitor all the different engine signals. You can see just an example in a couple of graphs here, and you can see our monitoring room in Winterthur to the left, bottom left, where we have a very modern infrastructure to follow up and support owners and customers in case of any troubles in service. A few words on the gas utilization rates as experienced now of these the first 3 vessels that have gone in service. You see this bar chart with different colors, which indicate the use of fuel oil in purple, LNG in green, and MDO in light blue. And you can see the bars actually represent different ports. So on the maiden voyage from Asia to Europe, all these 3 vessels were operated primarily on fuel oil or MDO. That's the first bar or first couple of bars. And after first bunkering of LNG, the green bar starts to ramp up. This is the utilization of LNG. You can see on the first vessel, Jacques Sardet, the typical utilization rate was about 83, 85% there. We have seen a couple of issues, actually not on the main engine, more related to controls of FGSS and other things that have sometimes prevented the engine to run on gas. But this was ultimately fixed, implemented on the following vessels from beginning, and you see that right after first LNG bunkering, these vessels have achieved gas running rates of 96-97% from beginning. So I think that is a very good result, proving also that the systems are actually simple and reliable to operate by the crew. Another example here related to carbon intensity, or in this case EEDI. What we see with this kind of vessel designs, just to mention an example, is that we have there is a chance to achieve very large benefits in terms of carbon footprint already now, in line with IMO's decarbonization strategy. So on these vessels, as an example, actually the 50% reduction compared to 2008 baseline is already achieved. So that is represented by this blue dot on the graph to the left. And we think that the interesting thing is that this is just a starting point as of today. So this is when running on fossil LNG. And as you see in the graph to the right, which is taken from a report from CLNG, we are at about 80% greenhouse gas emissions compared to a conventional engine running on low sulfur fuel oil. But by blending in of bio or synthetic LNG, as it was actually done on the first after the first bunkering of the first vessel, the emissions, greenhouse gas emissions, can be gradually reduced, of course, depending on the amount of bio LNG that is mixed in, but theoretically down to very, very low levels. So there is a good potential to even increase or improve this advantage in the future. And I think it's worth to note that this does not require any changes of the systems on board. So this bio or synthetic LNG can be absolutely stored in the same systems. The LNG supply systems are totally same, and no any modifications are required on the main engine for this. Then looking at air quality related emissions, so non-greenhouse gas emissions, which in fact are health relevant for human beings, such as NOx, SOx, particulates, for example. We see that this propulsion solution really offers the maximum benefits that are available today. You see in the graph, rather old graph actually that we have shown many times, but we have now the full proof from measurements also in service that these emissions are significantly reduced compared to a diesel engine, but also compared to a competing high pressure engine. So NOx emissions more than 90% lower, as we saw also in Dominic Schneider's presentation. Sulfur emissions almost inexistent, and significantly reduced particulate emissions, contributing to more healthy air conditions wherever these vessels are operated. So as a summary related to these engines in operation, 11 sets of X72DF engines have been job tested and delivered. 5 vessels are in service, as we saw, and we have seen good service or good experience in service without any major issues. We have had, of course, some smaller issues like oil leakages or so, which are rather normal and could be fixed without affecting any of the sailing schedules. We are monitoring the operation of vessels closely, also to give recommendations on how to improve operation if there is a potential for that. And we are, together with the engine builder, fully supporting the crew and the fleet management team to make sure that these engines run in best possible way. And last but not least, the The vessels, as we have seen, they are already in line with the IMO's 2030 greenhouse gas targets and have a potential to further reduce without any complicated measures. And before we finish here, I just have one more slide on another engine type, the X72DF, and the first project that we have for VLCC. So this is actually one of the last engines for completion of our dual fuel portfolio, where we have a project in China at the SIC in Dalian, where engine production is ongoing and will start testing very soon here. Two more projects are contracted in Korea, so also there good progress actually. So with this, I would like to thank for your attention. Thank you for listening, and hand back to SN Kim for the question and answer session. Thank you very much.
Thank you very much, Marshall, and also all presenters as well. And then also during your presentation, I have collected something and questions from the customer side, and then also I will invite you for the answers. Very hard at the moment, and also George, can you show your pictures in here? Yeah. And then okay, yes.
Hi everyone. Yes.
And then the customer wants to know when ICER diesel and will be officially announced into the market.
Very good question. We are WinGD is currently developing a solution for ICER diesel to launch. In other words, to launch also the application in ICER diesel mode. We expect the announcement to be made approximately around the middle of this year, so before the end of Q2 is our target. The reason for this to wait a little bit more is that we want to, when we do the announcement, we also want to have the GTD data available for the ICER diesel mode and some additional supporting documentation, and therefore have a complete package that we can give to customers.
Okay, and also ICER diesel mode can be prepared and with the integrated and with the engine body concepts.
So on engine, I guess that means
on engine. Yes,
well,
yeah.
In the first phase, no. This is also a very good question. Is something we are considering and have started to also look at, but this requires development. In this first phase, it will continue as an off-engine solution.
Okay, and also for the retrofit of ICER in serviced vessels and a certain case long route concepts of ICER that is to be required in the serviced vessels, and what is our idea and also what is our planning of this one?
We don't have a concept yet ready. However, we are preparing. We have been discussions with shipyards where we have looked at an alternative route that would make it easier to potentially proceed with a retrofit of ICER on board a vessel. But there's nothing yet officially released. It is possible. We have investigated based on inputs we received from the shipyard, some very good inputs, and we've given initial approval confirmation that alternatives are available that could enable in practice to carry out a retrofit. But the details of that of the concept is still being looked at.
Okay, and then the last question to you, and there are three kind of operation mode. One is, and one of them is combustion stability mode, and additional cost is to be needed for this
No,
operation
no.
mode,
The
or-
combustion stability mode will be part of the scope of supply, the standard scope of supply, and will be implemented in the engine control system, the engine software package. So it'll be one of the modes that'll be standard, because it is a mode where, in case the ICER is malfunctioned or there's any problem with the ICER, we want to ensure that the engine can still run in gas mode if this is required. Of course, there's always the option, of course, to run in diesel mode, but we want to enable also the option to continue running in gas mode. And with the combustion stability mode, even without ICER, we ensure that we can stably run the engine over the entire load range in gas mode, even without ICER. And this will be part of the standard scope of supply.
Okay, thank you, George. And also I want to invite Adrian. And the customer wants to know about the fuel consumption and the fuel consumption point of view, and between the 0.2 and the 0.1 on X72 0.2 and 0.1, 2.2 and 2.1.
Yeah, okay. Thank you. That is a good question. We are at the moment calculating the results which we will have for the 0.1 and the 0.2 engines. In the preliminary announcement, they were now released with let's say copy-paste figures taken over from the 72DF. But with a higher compression ratio, we anticipate some savings on the fuel consumption side. We, however, have no firm results yet. These should become available in course of the next couple of weeks, and we intend to reflect it in the next GTD release or upgrade targeted end of March.
Okay, and also what is the big differences between the WISE and also UNIC control systems?
The differences between the UNIC system as today and the WISE are of course on the hardware side, but also on the functionality side. WISE is much more powerful and let's say also contains new features, enhance the operators let's say interaction with the system, touchscreen and so on. The LU which we have on the UNIC system, Wärtsilä and let's say Heritage in comparison is quite small, and I mean WISE as such is a state of the art of the new generation engines. So this will contain quite a lot of benefits. And we have also seen in the presentation from Marcelot, service experience with the WISE is actually excellent on the 92DF fleet.
Okay, thank you. And also one more things to you, and also one of our customers wants to know how much cost can be reduced by the 0.2 version of X72DF.
Yeah. Of course, a very valid question, although difficult to answer because we are not, let's say, making the cost. We see the engine will become significantly lighter, saving several tons. But let's say to evaluate the exact cost saving potential, it would be better to ask the engine builder, who knows how much his engines cost. So I cannot clearly answer that.
Okay, thank you very much, Adrian. And then you, Dominic, and and also you know well, all of our customers is knowing that the N2O is one of greenhouse gas emissions at the moment, and also the IMO is considering to adopt the N2O emission as well. But just before you have mentioned and shown a certain material, and I know X is also one of a greenhouse gas emission one.
Hello?
Oh.
Very.
Yes.
Yes, NOx has a global warming potential, which is now investigated in the IPCC panels. The IMO panel investigating the various species causing global warming. NOx cannot be neglected, as latest study shows, and this is now being addressed also at the IMO if this needs to be considered in future.
Okay.
It's not yet in
Okay.
the discussions with the impact panels, for example, but we expect it to come sooner or later.
Okay, okay. Thank you very much for your reply. And then, and also Lodi, that is the last invitation for our customers' questions. And then at the moment, you know, well, IMO, greenhouse gas emission is very focused on the IMO and EU as well at the moment. Yes, and everybody is knowing about the greenhouse gas emission, and with the XDF is not so competitive at the moment, and with Otto cycle, and this is a big influence on the bigger blowers instead of smaller blowers, and in fuel consumption and the greenhouse gas emission. In this regard, a customer wants to know, and what is the next planning for the further improvement of XDF to meet the greenhouse gas emission level and also methane slip and the other things as well.
Yeah, this is right now under the introduction, and this is ICER. The target there is to reduce gas consumption and reduce methane slip, and both of them together will reduce the greenhouse gas. And I think it's quite a big step. You have seen in part load, we save a few % on consumption, and we halve about the methane slip. So we get far above 20% in total greenhouse gas reduction compared with diesel engines. So this is right now what we have to do in the next 2 to 3 years to expand it to the complete portfolio. And about the next step, I cannot tell you anything right now because we have not decided for another announcement. And I think it needs, of course, much more R&D work. But we think we have taken a step now with this ICER. Thank you.
Thank you, Rudy. 경청해 주셔서 대단히 감사합니다. 우리가 약속한 시간이 그 5시 반이기 때문에 1분 지났습니다. 1분 지났는데 또 추가적으로 그 질문할 내용이 있으시면 우리 그 마케트인 신준함 대리나 저희 그러니까 윈지디 코리아 멤버들한테 이렇게 연락을 주시면 그게 따라서 우리가 또 답변을 드리도록 그렇게 하도록 하겠습니다. 2시간 동안 경청해 주셔서 대단히 감사하다는 말씀 다시 드리면서 저는 물러나도록 하겠습니다. 감사합니다.
Yeah. Thank you everyone for today's presentation. 오늘 시간상 다루지 못했던 Q&A 부분은 메일로 따로 연락을 드리도록 하고, 그리고 추가적인 질문이 있으실 경우 메일로 언제든지 문의 주시면 저희가 답변을 드리도록 하겠습니다. 또 웨비너 시작할 때 못 들으셨던 분들을 위해 다시 한 번 더 말씀드리겠습니다. 발표 자료는 상단에 있는 핸드아웃이라고 적힌 부분을 클릭하시면 PDF로 다운로드가 가능하십니다. 오늘 윈지디 웨비너를 통해 유익한 시간을 보내셨길 바라며 다시 한 번 더 참석해 주셔서 감사합니다. 수고하셨습니다.